Hello all, these are your notes for chapter 10. I decided to go ahead and do it in a notes section rather than doing it as a PowerPoint because this seemed easier and simpler to explain since the matter that is contained from chapter 10, 11 and 12 is very dense. So looking at this, we are going to review very quickly about the 6 steps of hypothesis testing that is being talked about. So the first one is state your null hypothesis. Remember that the null hypothesis relates to a pinpoint value. It could be a 0 or anything else. And so look over here, if you see that your null hypothesis, the mean of the population is 250. 250 is your pinpoint value. You also remember that it has to lie on the continuum and it cannot be the end values, the lower limit or the upper limit. Review chapter 7 PowerPoint and the video for more details, but I will still talk a little bit about here which is relevant to this chapter. The other one is, the second step was to state the alternate hypothesis, which is H1 or HA, which has to be always in the same form and opposite to that of the H0. We had talked about also the fact that the researchers generally set up the null hypothesis as a way to disagree with it. So when you state your alternate hypothesis, it is more in line with what the researcher thinks is going to happen. So if you look down at the example over here, H0 is the mean of the population is 250, but the alternate hypothesis is exactly the opposite of that statement and is in the same form with the mean of the population is not equals to 250. So basically your null hypothesis is a statement about the parameter of the population. And when we say parameter, remember we are talking about the word that is corresponding to the parameter, and this parameter is related to the population. And then you have your statistics, which is your mean M. Your M is for the sample, and whatever we gather, we infer and relate it to the parameter, which is the mean for the mu for the population. So your sample is inferred, your statistics that you get from your sample, and you make your inferences to the population. So it's like it's a straight line from the sample to the population, and you're making inferences there. This is the reason that I did notes, because we'll keep going up and down for me to be able to explain in depth about what this chapter was talking about. So the third step was about selecting your level of significance. Most often the level of significance selected is 0.05. It is the alpha. It is sometimes also donated using P. But it is the same thing. This lead symbol that you say is a Greek symbol that is called alpha. Sometimes we also see the alpha value or the level of significance is 0.01 or 0.001. So basically what happens is a researcher states their null hypothesis, states their alternate hypothesis, selects a level of significance, collects and summarizes the sample data. That means you have a sample, you collect data from it, you summarize the data using the statistics that you have, and then whatever value you get, you compare it with the level of significance that you have found. So if they are identical, that means the value that you collected is identical with the level of significance, they match up, obviously your null hypothesis cannot be rejected. If there is a small significance, if a difference exists but it is a small and that is within the sampling error, then once again you cannot reject the null hypothesis. But if there is a difference exists and there is a big difference, that means your p-value that you get is less than 0.05 or less than 0.01, or your F value is greater. Remember how we talked about you can have either the F value or the T value or the P value. Whichever one you do, it doesn't make a difference. You will get the same result. But if it is more, like a P value is more and the P value is less, P value is less and the F value is more, then we reject the null hypothesis and we say that there is a statistical difference between the results obtained, and these results shows that there must be something happening there. If I would and so here is where you make the decision. So for example, if you are looking at, I'm going to take an example of comparing athletes and non-athletes. You may be comparing anything about athletes and non-athletes. Let's say you compare about their GPA, the number of hours they study, or anything like that. And so you're comparing them. Here you have two variables, athletes and non-athletes, okay? But if you compare them and you see that the level of significance 0.0 is less than 0.05, then you say that there is a statistical difference between the number of hours they spend studying. So this leads us actually to the next part that I wanted to talk about, was the variables. Remember, if we have one sample that we have collected from the population and that gives you one variables, then you have one M. But if we have two variables, that means you have M1 and M2, which means it's leading to mu1 and mu2. So let's look at these with examples. So now one variable example is, suppose N means the number. Small n denotes the number of people, or number of objects, or number of levels of data that you are collecting. So here your n is number of people in the population, that is your 25 boys. And you want to collect the height. You're going to talk about the height. The average height is 145 centimeters, like one of the heights is 145 centimeters. So the average is 145. That means there are some high, there's some low, and all those things. But you want to infer, you want to say that mu is equals to 150 centimeters. That means you are hypothesizing the hypothesis that you do, the null hypothesis, is equals to 150 centimeters. Remember how we talked about that we set up the null hypothesis in a way that we want to reject it. So we know that the average height is 145 centimeters. So I am setting up as a pinpoint statement as 150 centimeters. Now this is going to lie on my continuum. So I know for sure that it would not be one of the n values over there. So the alternate hypothesis then would be that mu is not equals to 150 centimeters. The things to notice about this is the fact that here you have the mu. That means you are talking about the population that the sample has been collected from. You are inferring it. What the values of the population means will be by the way, so that you will go back and tell what inferences you make. Looking at the figure 10.1 on page 205 of your book, Hug, you see that once again this is the population and we extract a sample from the population. We have talked about the different ways that you extract the sample for the population. It could be a simple random, to going from a non-probability statistics to being a convenient sample or a purposeful sample. Whichever way you have extracted the sample has to be the representative of your population so that you can make inferences. So your sample average was 145 centimeters as an average height. So you are making references to what will be the mu, that is the average or the mean or height of the population of the boys that are there in the big population. This is once again when we were talked about is we are talking about one variable. So now we move on, or before we move on, we need to talk about the confidence interval. That is really very important. So the confidence interval is basically gives us a feel of how trustworthy the sample mean is. Remember how we talked about that the confidence intervals are built, like if you keep on extracted samples from the population and you plot them, you plot their mean. So this is about the different samples that you are taking from the same population. So and that's when you get your lower limit, lower bound and the upper bound, and which basically means that if you extract another new sample from the population and you do the statistics, the mean and all those things, it should lie within the range. So if the study is replicated with another sample taken from the population, we would expect sampling error. There's always going to be some sampling error, but confidence interval gives us the range within which we can expect the next sample mean to be there. So smaller the range, that means your samples are more representative of the population and they are closer together. And bigger the range, that means that each of the samples that you're extracting is not representing the same thing. So once again, there is interval estimation that we have talked about the last time. Please review those if you have any questions about that. I also wanted to talk about, in general, what would one variable look like. So in general, the null hypothesis for one variable would be mu is equals to a. Now a could be a 0, could be 150, could be any point, which is a pinpoint value. And then h1 is equals to mu is not equals to a, which is in the same form and opposite of the null hypothesis. There are two procedures that can be done to calculate the statistics part of it. One of them is the t-test given by the William Gossett. This is also called the student's t-test because when he was writing, he wrote a lot as a student and he did references for students and things like that. So basically it's also called a student's t-test and it is the more common one of the ones being done. And the other one is the z-test. To understand the t-test and the z-test in more details, we are going to look at the excerpts from your book 208, the page number 208, 10.3 and 10.4. So let's first look at 10.3. The 10.3 is actually a z-test. It says one sample z-test. So once again, you know it is a one sample. That means there is one variable there that we are using. Was used to test the statistical difference between the autistic children and the Japanese standard value. So now they want to compare the autistic difference in Japanese standard values. So your null hypothesis was that your mean would be equal to the government value. That means it would be equal to the Japanese standard values that is given. But your null hypothesis stated that the fact that mean would not be equal to the government value, that means it would not be equal to the Japanese standard value. So if you look at it, it shows you that z is equals to 0.90 and p is equals to 0.366, which means that your p is not less than 0.05, and hence there was no statistical difference seen between the mu, that means between the value collected and the government value. That means they fail to reject the null. And this means that when we reject the null, like I said, it means that there is no statistical difference between the mean and the government value. One of the things to notice about 10.3 is also that they do not really state the null hypothesis and the alternate hypothesis. In most cases, researchers will not state the alternate hypothesis. Quite often, they state the null hypothesis, but this researcher did not explicitly state the null hypothesis, but we can gather that that is what they wanted to see, is whether the mean collected is equals to the government value. Now, it could have been stated in the sections prior to this, but not in the part that is given over here. Let us now look at 10.4, which is the t-test. So if you look at it, it is talking about the mean estimate of the number of drinks considered indicative of heavy drinking for Kevin was this, and then one sample t-test. So once again, it is a one sample t-test, that means one variable revealed a statistical difference. The thing to notice is this one, t parentheses 179 equals to 6.35 and p equals to 0.001. So the first thing we notice is p is less than 0.05, which means we can reject the null. So that means that there is a statistical difference between the heavy episodic drinking and the drink and all that things. But what I wanted to talk about is the fact of this number within the parentheses. This number within the parentheses is actually called degrees of freedom, which is abbreviated as DF. The degrees of freedom for a t-test, if you add 1 to the degrees of freedom, or it is basically degrees of freedom is calculated by taking the total n, which is the number of data points in your sample, and subtracting 1. So the degrees of freedom would tell you that the sample size for this t-test was 180. That is what was looked at for the sample size. So here, when we reject the null, because the null hypothesis, if you look below it, it says the null hypothesis was equals to 5, the level of drinking chosen, because there was an agreement in the literature that consuming 5 drinks at one sitting qualifies one to be heavy drinker. But here we have rejected the null, so it doesn't mean that 5 should be the number of drinks consumed before the person is called a heavy drinker. Now, this experiment doesn't tell you what is the number, but it tells you that that 5 is not really a number. There is a statistical difference about the data that has been collected. So that is one of the things that you want to think about is when you do the statistical analysis or quantitative analysis, it's not telling you the how or what. It is actually telling you the why. Like there is a difference between those things. So we are going to review back a little quickly before I go on to the 2 variable samples, since that is one of the new things that would come up. So we already talked about the 6 steps of hypothesis testing. The hypothesis testing is the mean of the population. I apologize, this should have been H1. It is the alternate hypothesis. The mean of the population is not equals to 250. Your sample has the statistics and parameter is associated with the population. 1 variable, and then we have 2 variables here, which we will see in just a minute. If you look at this figure, you collect a sample from the population and then your sample mean is given. You make a null hypothesis about the population mean and hence you are making inferences about the population for it. So this is your diagram. Your confidence interval has a lower bound, upper bound, which means if we replicate the study and we take another sample, the means that are calculated or the statistics that are calculated will lie within this range. T-test and Z-test, we've just talked about Z-test and T-test. You really don't need to know the nuances or the formula for calculation. What you need to know about the degrees of freedom, the level of significance, what is the test being done, how to interpret the results, and things like that. So let's now talk about two variable examples. So if you have a sample but you actually have two variables, that means you have two mu's or two means in it, and you want to make inferences, then this is how it is done. So when you look at page number 212, you see there are two examples of it. The first one is about independent samples and the other one is about correlated samples. So the independent samples is, so if my two variables are independent of each other, these are also called unpaired samples, uncorrelated, unmatched samples. An example of independent samples would be, let's say, boys and girls. They are not correlated to each other. I have a sample that has all the students in it, and I have two variables, boys and girls, and I want to look at their IQ. So I could do the IQ. I want to compare the IQ of the boys and I want to compare the IQ of the girls. And that is what I do with the two variable testing. This is again quite similar to the studies like when you are comparing between dyslexia and non-dyslexia students, or you're comparing between athletes and non-athletes. Now here I am talking about independent samples. I'm talking about that they are not related to each other. But when you do your sampling, you have to be careful about it is, are you doing matching? That means the dyslexia students that you choose are matched to non-dyslexia students that you are choosing. So if that happens, if the samples are correlated, then there is different type of statistics done. So if you look at the first one, I have a population 1 that collects a sample. I have a population 2 that has a second sample. So I want to compare between these two populations. So my population was all the boys, all the girls, and then I collect a sample of the boys and I collect a sample of the girls, and they are independent of each others. I have my mean for the boys, mean for the girls, and I make references of what should be the mu for the boys and mu for the girls. So the second one is whether the samples that you have, the variable 1 and the variable 2, they are correlated to each other or not. If they are correlated, they could also be called as paired sample, matched sample, dependent samples, or within samples. There are different ways of correlation. For example, you could have the same group of people. So suppose like you are doing a pre-test and a post-test. I want to find out, like if I am doing an algebra test on the students, I give them a pre-test and then I do my instruction and then I give them a post-test and I want to see their gains on it. So that means my sample is the same group of people, which means that they are correlated to each other. Another way of doing correlated samples is matching. The matching is done is when you have a group, you have the first group and you recruit the second group because of the people in that group are a good match for a particular individual in the first group. This could be done with heights, could be done with IQ, running speed, or any other amount of variables. For example, I choose a group of African American females, and then I choose a second group of African American females because they match, or my first group contains ethnicities of 10% this, 5% this and this, but my second group is also has ethnicity to be the same like that, because I want to compare those groups. So then again, these samples are correlated. Again, like an example is, if you choose athletes and non-athletes, and your athletes, you decide that you're only going to have male athletes between these ages, or who have been in the college for this many years, and then you do non-athletes for comparison, you're again going to it has to be male students, it has to be within this, has to be so many years in college, or so many years in school, and things like that. So that is what is called matching. The third way is also genetic similarity. For example, that if you have twins, biological twins, one of them, you split them up, and one is a member of first group and the second is a member of the second group. This situation is quite uncommon, but it does happen. So like your example, dyslexia versus non-dyslexia students. I just took some of the examples from the various courses, that is various things that you guys are doing. Is now, if you are just comparing dyslexia and non-dyslexia students and they have no relation to each other, then that is different. But if you choose dyslexia students and you say that they had to be second graders, they had to be something like this, and then you choose the second sample of non-dyslexia students that match them in demographics, age, and all the other things, then those two samples are correlated to each other. So like when you look at this example, this figure here is a very good example to explain it. So you have a population 1 and a population 2. You have a sample 1 from population 1 and you have a sample 2 from population 2. But do you see these lines, these dotted lines that are going? That means they are correlated to each other. And then you have calculated the mean for sample 1 and mean for sample 2, and you now are making inferences for mu1 and mu2, which is your population means. So these are the things that you have to remember about. Very important to decide whether your variables are independent or whether they are correlated to each other. So like this one is definitely pre-test and post-test is given to the same student, so they are very much related to each other. Another thing to consider about is over here, what we're talking about, what you see is the dependent variable. So if suppose I am collecting data on males and females, which is my nominal data, but males and females is my independent data, independent variables, and I am collecting about IQ on them. So the IQ depends on the person, and so those are my dependent variables. So my statistics is actually done, or my inferences calculations are done on the dependent variables. Remember how we talked about earlier that to do all the standard deviation and all the analysis, your data has to be either the interval data or the ratio data. So that is what is going to be the dependent variable. So if you look over here, we have a pre-test and a post-test with student 1 that gives you 75 and 79. So this is my dependent variable, and my student 1, 2, 3 is just my nominal data, and then we have this to be my dependent data, which is my ratio data, where all my statistics will be done. So let us work with an example so that things become much more clearer. So the example that we are going to be looking at is about the heights between boys and girls. So boys and girls, we have n is equal to 20 boys, n is equals to 20 girls. Boys and girls are our two variables. That means so we are looking at the height, but we have two independent variables here, and there are two samples here. So when we talk about the null hypothesis with them would be that the height of the boy is that mu of boys is equals to the mu of girls, while the alternate hypothesis would be it is not equal. Now, one of the things that we have been talking about is how the null hypothesis gives you a pinpoint value. Here it is not giving you a pinpoint value, so it could actually be written as mu1 minus mu2 is equals to A or is equals to 0 here, because we are assuming that the heights of boys and girls, the mean height of boys and girls are the same. And then here it would be mu1 minus mu2 is not equals to 0. When we go forward and discuss the chapter 11 and 12, we are going to talk about samples with more than 2 samples. That means we are basically going to talk about 3 or 4 means, and in which you would have that mu1 equals mu2 equals mu3 equals mu4, because we cannot put it in a statement that is mu1 minus mu2. In that case, I will revisit the fact that null hypothesis is still a pinpoint value because of the variance. But right now, if we look at the 2 variables, we say mean of boys is equals to mean of girls is my null hypothesis, and it is not equal is my alternate hypothesis. One of the things that is very important to think about is how is your alternate hypothesis written, whether it is one-sided, one-tailed, or whether it is two-tailed. So that means whether it is directional or it is non-directional. If my null hypothesis is stating that mu1 minus mu2 is equals to 0 or it is equals to a pinpoint value, then one-tailed would be mu1 is greater than mu2 or mu2 is greater than mu1. That means I am stating that the mean height of boys is greater than the mean height of girls. Remember how our alternate hypothesis is what the researchers actually think should be the case. So in this case, if I say mu1 is greater than mu2, which means that the average height of boys is greater than average height of girls. If my results show statistical significance, then the significance would be the fact that yes, there is the height of boys is greater than height of girls. But if it doesn't, I cannot say that in some cases height of girls, or there is a difference between the height of boys and girls. It would be more directional to say that height of boys is more than the height of girls. Two-tailed or two-sided is when you say that mu1 is not equals to mu2, or mu1 minus mu2 is not equals to 0. That means the height of boys can be more or height of girls could be more. Let me give you an example of this. For example, I'm going to take an example about math. You are teaching students, you do a pre and a post test on the students. For the pre-test on, let's say, the concept of place value or counting. You do the concept of counting, you do the pre-test, and then you teach the concept, and then you do the post-test. So if I am experimenting to see whether the intervention or what I taught had a difference, I am going to make it a directional one, saying that the students' post-test results or the mean score of the post-test would be higher than the pre-test. So this is what is called a directional hypothesis. Or in the other case would be if I would start making, let's say, groups in the classroom, and I do different kinds of group, ability grouping and all different boys and girls groups and things like that, and then I want to look at a concept before and after, I could say that the grouping had an impact or didn't have an impact. So I am looking at both of those things. It is a non-directional or two-tailed. A question you would ask right now is, why do we even need to do is the alternate hypothesis to be directional, one-tailed or two-tailed? It is because your t-test or the test that you do has different values for direction and non-direction, the table. You don't need to know about the how to find the value on the t-table, because that is not covered in your intro to research class. But you want to know is whether the um, test or whether the experiment has direction or non-direction. It is one-tailed or two-tailed. So let's look at page number 214 for your excerpts 10.8 and 10.9. They are both talking about a t-test. Remember how we talked about the degrees of freedom? Now on the first case, when we are talking about degrees of freedom, this is independent samples. So when you have independent samples, the total amount of data can be determined by adding 2 to the t-test is degrees of freedom. So you just add 2 and that gives you the t-test. But when the sample are correlated, then you add 1 to the t-test of degrees of freedom. So looking at that, when we look at the excerpt 10.8, you see that they are independent samples. So if you want to calculate the number of data in it, or the number of people in it, or number of objects in it, you take 133 and you add 2 to it, since it is independent samples that are considered, and that would give you 135. But if you look at 10.9, it is a pre and a post test. That means it was given to participants that are the same. Remember, this is what we call to the same group of participants, and our sample size is correlated. So in this case, our sample would be 57 plus 1 equals to 58 students. Now let us look at the 10.10. One of the another type of statistics that can be done is the F-test. Your book talks about that the F-test is used, but it is slightly more biased in the sense that the probability of type 1 error is more. Remember what type 1 error is the fact that we reject the null even though it is true. However, whatever you do, like a t-test, F-test, Z-test, whichever test you do, you still get the same result. It is identical. So let's look at 10.10. Here, if you look at your F has 2 numbers in parentheses. Your 2 numbers, once again, this is your degrees of freedom. You add them together and then you add 1 more to it, which will give you your total data set. So in this case, you have your mean, that is M, which is the sample mean, your standard deviation, then your mean for the other sample and the standard deviation, and then the F comes out to be 8.510. P is less than 0.05. So this says that there was statistical significance on their experiment, and they reject the null. Let us look at another example of 10.11, in which again, if you see the F, you are actually going to see a table there. Some researchers would put a table in the article or in the study that they are writing about, and some would just write it in a sentence the way it is given: F1 comma 406 equals to 26.37 and P is less than 0.0001. So if you look at the table, you're seeing the degrees of freedom would be, you add the 2 between the groups and within the groups, which gives you 407, and then you add 1 more to it, which will give you 408 as the total set. We will talk more about the data set, but what I really want to focus on what it says on the top of the table, which says table 6, one-way ANOVA. What does ANOVA stand for? ANOVA stands for the analysis of variance. It focuses on the means, and that is why if you look at SS, which stands for the sum of the squares, and then you also have MS, which stands for the mean square. So it actually takes those into calculations and gives you a value of F is equals to 26.340. You don't need to know the calculation right now, but we do need to talk about what is ANOVA. So as I said, ANOVA is analysis of variance, and here the words to take care about is one-way ANOVA. There are many different kinds of ANOVA, which is what the chapter 11 will cover, but if it doesn't specify which type of ANOVA it is, then it is the one-way ANOVA. One-way ANOVA is related to when you have one independent variable and you have one dependent variable. That means when you are when you are putting people into groups, we are putting them one way or the other way, like girls or the boys. They differ only in one aspect, like gender. So that is what is called one-way ANOVA. You're considering just one thing when you are putting people into one or two groups. The part about ANOVA will be continued in chapter 11, but for chapter 10, these are the main aspects that you guys need to be knowing. All right. Have a great day.